So, good evening, everyone. I'm Calvin Paul Joseph, and today I'll be conducting the week one problem solving and doubt clearing session for the course State Space Approach to Control System Analysis and Design. So, this course was taught by Professor A.P. Tiwari of IIT Mandi. So, today, this session, I'll be talking about what is a control system, why do we have the state space representation of systems, what is a series RLC system, and also about the op-amp based system which Sir taught. Also, then usually in real life practical examples, the systems we consider are non-linear. So when we have a non-linear system, what we do is around the operating point, we apply a linearization. So how do we do linearization around an operating point? I will show with an example, and then we will see various other examples. Okay. So I would like a confirmation from you both that you guys are able to hear and see the screen properly so that I can proceed with the further parts of the session. And it would be good that if you could keep it interactive, you could tell what questions you have, what doubts you have, so that I can, conduct the session accordingly. Mm. So it'd be good, like, okay, yes, Vijay, Lakshmi, you can tell something. Like you can unmute and you can ask, answer and everything.
Um,
Sorry, it's clear,
Actually,
right?
the problem, how you will be solving the problems as per the assignment questions or like as per the syllabus like that?
I'm not allowed to solve the assignment question. So I'll be like, from what sir has taught, some things I will do a recap, and I will some steps which sir has skipped that I will show, and then I will talk about the basics of matrices, what is the state, what is the order of the state, all those stuff like that. So
Okay, fine, fine.
what would you be kind of looking for through these sessions?
No, actually, I thought I have studied this control system and modern control system in my UG and PG. So I thought I
Okay,
can explore more like that. So
okay.
whatever you're thinking to taught today, teach today,
Uh-huh.
you can go ahead and you can teach. If I'm having any
Okay,
doubts, I'll ask you in middle.
okay, okay. So you're a PhD student.
No, no, I'm a faculty in Rajalakshmi Engineering College.
Okay, 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 fine, fine. Okay, all right. Then what about others? Does anyone else have any suggestions or doubts? Okay, so then I'll start with the session, right? So the first thing which we are like, why do we do state space analysis, etc., is because we want to analyze a system, and when we want to analyze a system, the objective is we want to control the system. So basically, we are working on based on the control systems perspective. Okay. So we are basically working based on the control system perspective, and we have various systems are there. Okay, so there are various systems, and what we want to do is we want to control them, and when we want to control them, we need a model of the system. So we do what is known as mathematical modeling. So as Sir has taught, he has derived the equations of the system based on first principle. Okay, he has used first principles to know like how a system behaves. Based on that, he has written equations, and from those equations, he has got what is known as the state space representation. Okay, so the state space representation is for linear systems or non-linear systems. Can anyone tell? Okay,
Sorry,
so
can
like the
can
state
you please
space
repeat the
represent
question?
the state space representation of a system is for linear systems or for non-linear systems?
For linear systems?
Okay. Like usually we should do it most of the time for linear systems, but it can be made even for a non-linear system as well. Okay.
Okay, fine.
So once we what like sir has followed approach sir has followed is found the equations, and then uh, if the system is linear, he directly writes the state space representation of the system. Otherwise, if it is a non-linear system, what sir has done is he is linearizing around an operating point. Okay, linearizing around an operating point, and once he has linearized around the operating point, he is writing the state space representation. So then the state space representation for a linear time invariant LTI system is given by this way: x dot is equal to ax plus bu and y equal to cx plus du. Okay. So we will first consider a very simple system, okay, which is a SISO system. SISO system stands for single input, single output. Okay. So what are this A, B, what is C, D, etc.? These are matrices. And sorry. So these matrices we will generate for a system. So I will start with a simple system that is known as the series RLC system. This is where you apply your input voltage. Okay. You have your resistor here, you have your inductor here, and you have a capacitor here. And this is the current flowing over here. And the output is represented by this B output of T. Okay. So how do I begin analyzing the system? Like what should I do? Can anyone tell what is the approach I should follow? Hmm? Anyone has suggestions? So like first we do the mathematical modeling. We have my input. We will apply KVL. We apply Kirchhoff's voltage law to the system. We have my V input minus I into R minus the voltage across the inductor is minus L di by dt, and the voltage across the capacitor is given by minus 1 by C integration of I into dt equal to 0. Okay. So if you guys have any doubts, please you can stop me in between and you can ask your queries. Okay. So don't hesitate. You can interrupt me and ask me questions and try to keep it more interactive, etc. So that I can also understand when you're understanding, when you're not understanding and everything. Okay. So this is a representation of it. So this system has, so this equation has both integration and differentiation. Okay, this is my integration part, this is the differentiation part. So they what they do in such scenarios is, we know that my I is my current. It is equal to the rate of charge. So I is equal to dq by dt. So my integration of I into dt is also equal to q. Okay, we will use this concept in the further things. And also if we do di by dt, it actually is double derivative of the charge with respect to time. Okay, so with all these things, with all this information, we will substitute in my previous equation. What I will get is B in minus R into dq by dt minus L into d2q by dt T2 minus 1 by C into Q is equal to 0. So this is the equation. So now let me rearrange this equation. I will write it in this form. L dtq by d2t plus r dq by dt plus q upon c is equal to Vn. Alright. So till here, are there any queries? Any doubts? Okay. So let us consider. So what is the order of this differential equation? So this is actually, you can see it's a differential equation. And what is the order? Hmm? How do we determine the order of a differential equation? Give many of you are there, Bindu, Kavipriya. Okay. So the order of this differential equation is 2. Okay, it is a second order differential equation because it is d2q upon dt2. So it is the second derivative. So the order is 2. That is the highest power of the derivative is the order of the system. And if the system's order is 2, that means in the transfer function also we will get s square, etc. and further along. Okay. So this is the differential equation. And now what we will try to do is we will try to find a state space representation. So in the state space representation, what do we have to do is we have to consider state. So one state, let us take the state x1 to be q and the state x2 to be q dot, which is dq by dt. Okay, so this is the state. Now we will rewrite this equation in terms of these states. And we will also consider another thing is my u, that is my input to the system is Vm. Okay, so this will be L of d of dt of dq by dt plus r into dq by dt plus q upon c is equal to v in. Okay, so this is d of dt of x2 plus r into x2 plus x1 upon c is equal to v in. So we get this is x2 dot L into x2 dot plus r into x2 plus x1 upon c is equal to v in. So how do we write it as x2 dot is equal to minus x1 upon lc minus r upon lx2 plus v in upon l. Hmm? Any queries till this? Okay. So if there's no query, so this is x2 dot. Similarly, we have my x1 is equal to q, right? My x1 is equal to q, and my x1 dot is actually equal to dq upon dt. And this actually is equal to my x2. Okay, so these are the equations which we will use to form the state space representation. So in the state space representation, we write x1 dot, x2 dot, this is equal to 0, 1 into x1, x2. So it is 0 into x1 plus 1 into x2. That is why my x1 dot is equal to x2. Okay. And my x2 dot is minus 1 by LC. So minus 1 by LC into x1 minus r by lx2. So minus r by lx2 plus my input, right? So it is plus 0 because in the first equation there is no term of the input. And here it is 1 by L into U. Because I assume my input is my Bn. Okay, so this is the state space representation of this. Now, what is my output? My output is my output voltage. It is the voltage across the capacitor. So, how will I write this voltage? It should be in terms of Q It should be in terms of Q and dQ by dt. It should be in these terms. So can anyone tell me what would be the expression for the output voltage? Okay, all of you seem to be very shy. Acha. So the output voltage actually is 1 by C integration of I into dt. So this is equal to Q by C. Yes. So this I can write it as x1 by C. Okay. So but now we need to represent in terms of x1 and x2. So we write V output is equal to 1 0, sorry, 1 by C0 x1 x2. Okay. Uh, so if you will see, my V output is x1 by C plus 0 into x2. So this is what is represented by this equation. And this is the equation of C. Okay, this is the C equation, equation of C. Oh, the C matrix, the C matrix. Right? Uh, and here D is 0. Here D into U, and here D is 0. Okay, so I hope till this point it is clear. Right? I hope it is clear. And I'd like to stress upon some points over here. That is, this state X, we write it as Q1. Sorry, not Q1, it is only Q. Q and dQ by dt. Okay. So this is x1 and x2. So this actually is in the real domain, it has a size of 2 cross 1. 2 rows, 1 column. Okay, my x is 2 rows, 1 column. Similarly, this is my A matrix and this is my B matrix. Okay. So in my A matrix, it has 2 rows and 2 columns. Okay, so this is the dimension of A. If you see my B matrix, it has 2 rows and 1 column. Okay, so my B matrix is 2 row, 1 column. And if you see my C matrix, it has 1 row and 2 columns. So my C matrix belongs to 1 row and 2 column. Okay, so this is the set, like the dimensions of the matrix. And you guys know, right, that we can only multiply. Suppose we have matrices P and Q. So, and P has some R P1 cross P2, and Q belongs to our Q1 cross Q2. And then we can multiply P and Q only. This can happen only when my P2 is equal to Q1. Okay. So these are some basics about matrix multiplication, etc. I just felt it is necessary to stress this because in further aspects of the course, Vesa will be teaching various like design and like observer design and pole placement and various other things that this concept of matrices is very important. So this should not, it should be clear. This fundamental should be clear to help you to do this course well. Okay. So what I have done is like I have written a MATLAB code. Okay, I have a MATLAB code I have for a series RLC system, and I have done it through charge based. Okay, so I will just explain what it is. So I have this line of code, which means what it means. It is I'm using this for generating like a transfer function, and transfer functions we write in terms of S. So I have denoted like this. This is the value of my resistor. This is the value of my resistor R. My L, this is the value of my inductance. I have set it to be 1 millihenry. And instead of using C, because it for a capacitor, I have just written as cap. Okay, so this is the value of my capacitor. Okay, so I have defined these variables, right? and this by A matrix. This is my A matrix. So let me run this lines of code in a step-by-step manner for you to understand. So these are things I have done for to help you understand and everything. So like what is a good way is you can do these derivations and you can try to see the response. And MATLAB is a very useful tool. I hope all of you guys have access to it. Right. So let me just take this line of code. So S equal to transfer function of S. So if I will run it, okay, this requires my control system toolbox. So sorry, actually I done it in my PC and in my laptop it is not there. I'll just install it 1 minute. Okay, so this is taking some time. Let me go back and let me teach further, and then hopefully this will get installed side by side. Okay. So till here, are there any queries? If you have any queries, you can ask me, or I can show another way of how to get the state space representation for a series RLC circuit. Let me. So this is a control system toolbox. Let me install it. Okay. Let me while the installation is going on, I will just like to add certain stuff. So I have taken the states as q and dq by t. So I have taken the states q and dq by t. Like, are these the only representation possible, or I can choose other states also? Like, can I choose other states? Hmm? What do you think? Like, you know that the transfer function from input to output is the same. I will have only one transfer function because it will be unique. But is the choice of state also unique, or I can have different states representations?
No, the current through the inductor and the voltage across the capacitor can be chosen as the state variables. Correct?
Yes, yes, we can choose that also as a state variable. So exactly correct. So what I want to say is like uh, transfer function from input to output is unique. This is unique, but the state space representation depends on the choice of states. Okay, it depends on which state I choose. Okay, so in our first example, what we chose q and dq by dt, or it is actually q and current. Okay, but as madam pointed out, we can also choose state to be the current through the inductor and the voltage across the capacitor. This also is a way, and this is more frequently used, because when we do measurements, etc., we don't see charge, we see the current, we see the voltage, we measure the voltage, we see the current flowing, etc. No one just like thinks in based of charge. Okay, so this is more practical way of representing a system. Okay, so we will also try to represent this. that. Just hold on. Okay, another point I'd like to add is like this Zoom meeting will end in 10 minutes and then I will again start this Zoom meeting. Okay, so in the same link, I will start the meeting, so don't worry. So it will go off and then I will again restart the meeting and you guys can also please rejoin. So hopefully this will install MATLAB. So what we will do now is, as we have this resistor, inductor, capacitor, we will try to derive the state space equations considering the state as x and IL. So this is my current and this is the voltage VC and the current IL. Right? And this is my VM. Okay. So now we have to derive this. So I'm extremely sorry for these disturbances in between. I was just hoping I should have checked actually earlier. Okay. So now we will try to derive considering the states IL and VC. So what is the equation? We have Vn minus I into R minus L di by dt minus Vc is equal to 0. So this is the equation. And we know this equation. So what we can write is, when we do state space representation, we consider only the first derivative. We want to represent the equations in terms of the first derivative. So we write, what do we write? L di by dt is equal to minus IR minus VC, right? Minus IR minus VC plus Vn. Okay. So now what do we do? The state x1 is I, the state x2 is VC, and my input is Vn. So we will write it as L into x1 dot is equal to minus x1 into R minus x2 plus Vn, right? So my x1 dot is equal to minus x1 into R by L minus 1 by L into x2 plus, okay, Vn actually should be U. So this should be my U and this will be U by L. Okay. So this is the first set of equations. Okay. And the next set of equation is, we want to find the voltage, right? Voltage across cap, across the capacitor. So we know the current is equal to C dVc by dt, right? So my dVc by dt is actually 1 by C into I. So this actually is my x2 dot, sorry, x2 dot is actually 1 by C into x1. So now if you see, this is my equation, let us say A, this is my equation B. So I will write it in my state space representation. So I will write x1 dot x2 dot is equal to, so what is my x1 dot? Is minus x1 into R by L minus 1 by L x2. So this is minus R by L minus 1 by L, okay, plus 1 by L into U. Okay, what is my x2 dot? Is 1 by C into x1. Sorry, over here you will get x1, x2. Okay, so now my x2 dot is 1 by C into x1 plus 0 into x2. And since input is not there, so this also is 0. Okay, so now this is my new A matrix and this is my new B matrix. It is a different matrix. Okay, and what is my output? My output actually is equal to VC, voltage across the capacitor. So this actually is my x2. So my y, I can write it as 0, 1, x1, x2. So this is my new C. So any queries in this or any doubts? Okay. All right. So now let me go to MATLAB. And as I was showing over here, let's move on quick trial run. Okay. So this is my series RLC thing, which I'll do by the first time when I use the charge and the current as the states. Okay, so this is for denoting S as a transfer function variable. This is the A matrix which I got. This is the B matrix, right? And this is the C matrix. Okay. And for the state space, like the transfer function, it is given by C into inverse of Si minus A into B. So this is the way I will get the transfer function. So what I will do is I will just run this section of code. So I hope you guys use MATLAB because it is a very useful tool. So what I've done is I've just initialized variables. I've given values to that. I've written the A matrix, B matrix, C matrix. Now I'm finding the transfer function from there. So what I will do is I will run this section. Okay, G charge is just Manoj ki G charge is just a transfer function. I've just given the name for the transfer function G charge because I have used it. Okay. So now let me just run this section. So I will run this section and then I will get my transfer function. You see, this is the transfer function I got. Okay, so it is a second order transfer function because as I said, there are two states, second order, and in the differential equation also it was order 2, and these are the values of the transfer function. Hmm. So this is one way I have written. And if you want like if it would be useful for you guys, then I could also, um, attach or upload this code also. I'll have to see whether it's possible. Okay. So this is the one using charge-based method. Okay. Now let us see. Also, we have derived another set. So this is for this matrices, for this C mat, for this A matrix, B matrix. I have used. Now I will use my new set of equations A, B, and C. So now series RLC, the current and voltage based states. Current and voltage are the states. So this is my new A matrix. As you see, minus R by L, minus 1 by L, 1 upon cap, 0, etc. This is a B and C matrix. And now this is GILVC is a transfer function when I'm considering inductor current and capacitor voltage. Okay. So now let me run this line of code. I can do evaluate selection in command window, or else I can also do run section. Both of these options are there. So let me just run this section. It is giving me same transfer function. If you will compare this transfer function and this transfer function, they are the same. Okay, they are the same. So thus, what was my objective was, my objective was the transfer function remains the same. The transfer function from input to output is unique. It is the same, but the state space representation depends on the choice of states. But the effective transfer function which you get will be remain the same. Also, I'll just touch a little bit of this MATLAB code which I wrote, like to just give a better understanding. So let me go back to this thing. Okay. So if you see here my A matrix, it is 0, 1, minus 1 by LC minus R by L. All right. So 0 is my first element. Then this is first row, second column. Okay. So and then I have in my second row, first column minus 1 by LC, and here's minus R by L. So how I write it in MATLAB is I will write, so I've written A. Okay. So this is 0 and 1. Okay, the 0 and 1. So what I could do is I do 0, comma 1. So that means it's the first row, first element, first row, second element. Okay, so first row, second column. Then I will do semicolon. Semicolon means I am going to the next row. Okay, I'm going to next row. And then I'm doing the second row's first element. So that is minus 1 upon L into cap. Okay, the capacitor I put. Then I give a comma again. Okay, and then I do minus. This is second row, second element. Okay, so this is how I write my A matrix. And if you see, the A matrix comes like this. It comes in this form. Okay, so this is how the A matrix will come. Similarly, like that, my B matrix is one, two rows, first one column. My C matrix is one row, two column. Okay, so this I just wanted to highlight how the matrices are written so that you don't make any mistake while writing them. Over here, actually, I could have added a comma, but also it still accepted it like that. Okay, so these are the matrices, and thus we have verified that both of them are equivalent. Transfer function remains the same, only the state space representation is different. Hmm. Now, let us, so then we have shown a MATLAB demonstration. It has been shown. Now let me teach regarding the op-amp system, which sir has taught. Okay, so sir taught about op-amps in which part? I think over here. Okay, so this is the operational amplifier. This is operational amplifier system which sir considered. Let me take a step of it. Okay, so this is the op-amp system. Okay, so now uh, what sir has done is he has found it in terms of Q1 and Q2. These are the charges flowing in those respective branches he has found out. But when deriving, there are certain assumptions which were made, which I'd like to point it out to you guys. Okay. So this is an ideal op-amp is considered. And in an ideal op-amp, and like can anyone tell what kind of feedback is there? Is it negative feedback or positive feedback? Hmm? Like in this setup, is there positive feedback or negative feedback? Okay, so you guys are very shy. So this is actually negative feedback. Okay, there is negative feedback because you can see the output voltage is being fed to my inverting terminal of my op-amp. So it is negative feedback. All right, and hence there is this concept known as virtual short or virtual ground concept. Virtual short or virtual ground. In this concept, what is assumed is that the voltage over here and this voltage over here is equal. That is, there's kind of like a virtual short is there between these 2 points. Okay, so there's a kind of like a virtual short between these points. So let's suppose this is my V plus and this my V minus. So because of virtual ground concept, what happens is my V minus should be equal to V plus. And what is my V plus voltage? Can anyone tell me what is the voltage at V plus? Please be interactive. So the voltage at V plus actually is connected to ground. So it is 0 volt. Okay. So that means my V minus should also be 0. All right. So these are the voltages over here. And then sir has written the equations that you can apply KVL here. So he applies KVL. He gets Vi of t, Vi of t minus I into R1 minus 1 by C1 integration of I1t into dt is equal to 0. And then what sir considered is, I1 is actually dq1 by dt. So you got Vi of t minus dq1 by dt into R1 minus q1 upon C is equal to 0. So any doubts in this? Like how these equations have come? Okay, so that's why I just wanted to stress regarding how this has come, because there should be a proper understanding regarding this. Many of you will know this also, most of you will know, but I just wanted to, brush it up so that you guys can understand how Sir is derived. And this course is not a very simple course. It is a little bit of an advanced course. So it's not like there is any straightforward formula which you can just use for any sum and get the result. It is also a bit of a theoretical thing that you need to understand the concept, because in the assignments which sir has provided, which they have given, there are certain questions which test your understanding of the concepts and the theory. So you need to understand the theory and you need to understand the maths behind it and you need to solve it. So there are certain things which I feel could be a bit blurry for you guys. So that's why I want to tell and highlight those concepts. Many of them you may know also, but just for safety, just for reinforcing the concept, I'm just trying to highlight them. Okay, so this is one equation which we have. Similarly, what Sir has done is he has got the equations for these things as well. Okay, he applied KCL and Q1 of t is equal to Q3 of t plus Q2 of t. Similarly, these voltages are equal and this voltage is equal to the output voltage. Based on that also he got certain equations. Okay, so these equations were derived. If you have any doubts in it, you can ask me. So that's how Sir derived it. So what is Sir has written? Op-amp is assumed to have infinite input impedance. Okay. And then he wrote all these equations, dq1, dt, feedback loop, he wrote the equations. Then in terms of electrical charges, he wrote it. Okay, this actually, there was a mistake. This actually is plus. This actually is a plus. And then it becomes 1 by C2 minus Q1, Q2. This is fine. Okay, and these are the expressions and this is the equation. Okay, so any doubts in this? Also, I'd like to tell you that it's best when when you're going through the videos, like those videos, I admit they are very big. Okay, they're very time consuming and all, but it's best that you like derive alongside Sir. Okay, so once you derive alongside with Sir, and there are certain things where Sir has directly gone to the final result, but he has told that you can do the intermediate steps. So please try to do the intermediate steps so that you can understand and get a correct background. So sometimes when there's a linearization, when there's a square root, like what is the assumption so that's used, I will be hoping to touch upon that. But I'd like to just, give you the idea that you should try to do it on your own. Okay, so these are the equations, and so has got a ABC matrix for this as well. So when for this, I have written the equations, the matrices. I have assumed some values of R1, R2, C1, and C2. I have assumed some values for them, and I have written these matrices in terms of that. And then I will again use a concept of G charge. Okay, the transfer function, and I'm just using charge. So let me run this. Control C, pasted it, I'm running it. So you will see that this is the transfer function which we are getting. Okay, this is the transfer function which we are getting based on these ABCD matrices, right? So now we have done through charge based method. Let us try to voltage based method. Okay? So what do we have is, this is my R1, this is my C1, comes with a negative terminal and positive terminal. This is connected to the ground. This goes to C2. So we over here, so let's put R2 first. So let us follow it. So this is the R2, right? And this is C2. So we'll consider, and this is my V input. So let us consider states plus minus Vc of t 2 plus minus Vc of 1. Okay, and this is my V output of t. So now the states I am considering it to be Vc1 and Vc2. Sir, I had considered the states to be actually Q1 and Q2, but these are the states I'm considering. So now how should I solve it? Hmm. So first I'll start with the input side. So I have my V input of t minus Vc1 of t upon R1 is equal to this current I1. Okay, this is current I1 of t, right? So this current I1 of t is actually flowing through my capacitor. And the current through the capacitor we know is given by C1 into dVc1 upon dt. So we can write the equation as C1 dVc1 upon dt plus Vc1 upon R is equal to V in upon R, or we write it further as dVc1 upon dt is equal to minus Vc1 upon R1 C1 plus V in upon R1 C1. So this is my equation A. Okay, and this this I can write it in terms of dx1 upon dt is equal to minus x1 upon R1 C1 plus V in upon R1 C1. And also let me write U is equal to V in. So this will be U upon R1 C1. Okay, any doubts in this? Okay, so now let us try to find for the output side. Okay, this VC2. So what do we have? So this is VC2. Similarly, this also is VC2. So let this be the current I3 of T, and there's a current I2 of T. We are following the same convention. And this voltage over here is 0, and there's a voltage V output, right? So if you will observe, my V output of T actually is equal to minus Vc2 of t. They're in the opposite polarity. So my output voltage actually is by negative of Vc2 of t. Okay. So now we have to find what is this I2, what is this I3, what is this I1. So first we'll apply KCL over here. When I apply KCL, what I will get is I1 of t plus I2 of t plus I3 of t is equal to 0. Okay. Now what is I2 of t? I2 of t is basically minus the output of t by R2. Okay, it's actually the output of t by R2, which actually is equal to minus Vc2 of t upon R2. Okay, this is the I2 of t. And what is I3 of t? I3 of t is C2 into minus of dV0 by dt. So I3 of t is equal to C2 into dV0 by dt. It is C2 into d of dt of minus Vc2. So I3 of t is equal to minus C2 dVc2 upon dt. Okay. So till here, is there any doubts? Hmm? So there are no doubts. I'll continue. Okay. So what we can write further is I1 of t is V in upon R1 minus Vc1 of R1. So that is equal to V in minus Vc1 upon R1 plus I2 of t is actually equal to minus Vc2 by R2, and I3 of t is C2 into, it is actually equal to minus C2 d of dt into Vc2 is equal to 0. Okay. Okay. So now what do we get? This C2 d Vc2 of dt plus Vc2 by R2 minus V of R1 plus Vc1 of R1 is equal to 0. So this C2 dVc2 by dt is actually equal to minus Vc1 by R1 minus Vc2 by R2 plus Vn upon R1. Okay. All right. So we can write this further as dVc2 by dt is equal to minus Vc1 upon R1 C2 minus Vc2 by R2 C2 plus Vin upon R1 C2. Okay, so this is the equation. And now we will write it in terms of the state space equation. We will get d of x2 by dt is equal to minus of x1 by R1 C2, then minus of x2 by R2 C2 plus u upon R1 C2. Okay, so this is the equation B. So we have our equation A, we have our equation B. In this we will write the state space equation. So we will write dx1 by dt and dx2 by dt. This is actually equal to, what is dx1 by dt? It is minus x1 by r1 c1 plus u of r1 c1. So it is actually equal to minus 1 upon r1 c1 0 x1 x2 plus u upon r1 c1. So it is actually 1 by r1 c1 into u. Okay. Similarly, dx2 by dt actually is equal to minus 1 upon r1 c2 minus 1 upon R2 C2 plus 1 upon R1 C2. Okay. So these are another set of equations. So this is another state space representation of the same system. Okay. And what is my output? My output Y is actually V output, which is actually minus VC2. So this actually is 0 into VC1 plus minus 1 into VC2. So Y is written as 0, 1, VC1 and VC2. Okay. So this is the new A matrix, this is the new B matrix, and this is the new C matrix. So till here, is it clear? Or are there any doubts? Okay. So all of you are very silent, Bindu, Kavipriya, Jayan, and Vinan. So please be a little bit more chatty and talkative, and let me get some feedback, etc. Also, you can tell me like from which colleges or what you are currently doing or what are you looking for from this course so that I can, teach accordingly and so that it can benefit you as well as me. Okay. So if you're too shy to uh, like unmute and talk, you can also send a message. All right. So don't worry. And also one more point I'd like to add is that this session is being recorded and this will actually be like through the protocol of NPTEL, what I have to do is I have to record these sessions, then I will merge them, etc. And then I will actually upload this video on YouTube to my channel, as well as the link to these sheets to whatever I'm writing also. These notes also I will upload it somewhere. Okay. So okay. Means multitasking. Fine, fine. Okay. So these will be uploaded. So I will share that link later. But I can actually currently share the link of this. Okay, this link I can share. So this is a link to my YouTube channel. Okay. So on this YouTube channel, I will be uploading this recording, this session recording. It will take some time. It immediately will not. I'll not upload. I need to record and I need to merge, etc. and all. But I will upload the videos on this channel. So afterwards, also after the session, if you have any doubts, if there's anything you missed, like many times you may miss the session, you may have poor network connectivity, etc. So you can go back and you can check the video at your convenience. Mhm. Yes. So I just like complete this thing. So these equations were also made for the one where we use the voltages, and these are the ABC matrices which are there, which are same as the one which we have derived. Okay, over here it should be minus 1. It should be minus 1. Okay, so these have been derived, and again, this was run, and we get this result. Okay, so I just like to highlight something. It is not very clear for you guys. So let me do one more thing. This is my G charge. Okay, if you will see, slowly let me move it. This is my G charge transfer function, and this is my G voltage transfer function. So if you can see, it is minus 10s square minus 10s minus 1.766 into E minus 15. So E minus 15 means what? So into 10 raised to minus 15. Okay, that is a very small value, which is approximately 0. So it is negligible. Okay, and this is the denominator, which is actually the characteristic equation of this transfer function. Similarly, my G charge again is minus 10s square minus 10s. Then it is again here minus 1.76 E minus 15. So this also is very negligible. And again, you can see the transfer function remains the same. Okay, s cube plus 3s square plus 3s plus 1. Okay, so which is the characteristic equation. So that's I just use these two examples which are easy so that you guys can understand like how the state space representation is non-unique, but the transfer function is unique and will remain the same. The transfer function from one point to another point will remain the same irrespective of what states I select. Okay, that flexibility you have. Hmm. So now let us proceed further. We will consider this system. Here, this is a simple spring mass damper based equations. So it is linear as well. So I'll not be touching this, but I like to highlight in this part liquid level in an open tank. Okay, so what is happening over here? There is a liquid being flow being sent, and there's a liquid also, and that liquid also has an outlet. There's an inlet, there's an outlet. So depending on the speed or the flow at which I put my input, as well as the speed at which the output is going, the height in the tank will vary. Okay, so this is like a very real world problem which you guys also have. Like in your house, you will have a tank. Okay, so you will send the water from the pump to the tank. And then when you open the tap in your house, like some water from the tank gets dissipated, etc. So if your tank is full, means your h of t height will remain be at the top. If your tank is empty, that means your height will be zero. Okay, and what you would like is the tank to be filled at some particular good amount of height so that you have backup in case the water supply is lost or something, that you have a backup water storage. Okay. So the goal and objective in this is that this height is changing. Okay. All right. So the volume of the liquid in this tank is given by this expression V of t is A into H of t. Okay, and you can see in this tank the area is fixed. The cross-sectional area is fixed. So the volume is the product of area into the height. Okay. And how this liquid will change, volume will change is given by this expression. Okay, so okay, I'd like to highlight this Zoom meeting will end in 10 minutes since we don't have the premium version of Zoom. So after this meeting ends, I will again restart with the same meeting. So this is the same link. So all you have to do is you have to rejoin the same link and you can join the meeting again. It will go as continued. Okay. So now these are the equations which Sir has written, which Sir has derived. Let us consider. So this is a simple system. This is an open tank system. Okay, open tank system. And these are the equations. So what has Sir has done? The change in the volume. Okay, is also d of dt into area into the height is equal to the q, the amount of flow, rate of flow flowing in and the rate of flow flowing out. Okay, it is given by this. Now since area is fixed, so it comes out. So it is a d by dt h of t is qi of t minus q naught of t. So what actually I prefer is I don't write these expressions t everywhere because I know that it's a function of time. So if I write it, don't write it, like it is kind of annoying. So I'll ignore it. Okay. So this is dh of dt. It is actually qi minus q0 upon a. Okay, so you must know that this qi and q0, they are not constants. They are still functions of time, but I'm not just writing in this. Okay, this is just something. A is a constant, but this qi and q0, they are not constants. So I just like to highlight that. Similarly, so that's shown that this flowing out is actually given by mu into square root of h. Okay, as you can see over here. This q naught is mu into square root of h, depending on the height. Okay, mu depends upon this nozzle, how it is, etc. So finally, what we can write is dh upon dt is equal to qi minus mu square root of h upon a. So dh upon dt is equal to minus mu by a square root of h plus qi. All right. So this is my equation. So what is the order of this system? Like what is the order of this differential equation? Hmm? Kavipriya, Jaya, Bindu. You can text, you can send a message.
First order.
Yes, correct. Very good. Jaya, and thank you, Kavipriya. You have sent it. So this actually is a first order system. Okay. It is a first order system. Okay, so now, is it a linear system?
No, it's a non-linear because of the square root.
Yeah, so it is a non-linear system. So now what is the method which Sir is using is, he first will consider a steady state operating point. Okay, there are something known as a steady state operating point. So steady state is like equilibrium. So what do you mean by equilibrium? Equilibrium means you have reached the final, like a kind of, you have reached a steady point. You have settled somewhere. Okay, there's no more changes. Okay, like everyone wants to get settled in life fast and everything, but hey, you can never settle in life. That's something else. Okay, so what is assumed is the height has reached a steady state operating point h naught. The area remains the same. Okay, area is constant, so you don't have to worry of it. The qi, okay, it has reached some value, and the q naught has reached the value q naught, q out 0. Okay, qi is 0, this h 0. This is the steady state operating point. So is qi 0 equal to q out 0, or is it not equal? So my qi 0 is actually equal to q naught out 0. They have to be equal, because if they are not equal, then the height will change. They are equal. So that means, if you see in this, the amount of liquid flowing in should be equal to the amount of liquid flowing out. Then only the height will remain the same. So let us see, like if you think, imagine the tank on your house. Like if there's no water flowing in and if there's no water flowing out, no tap is open and the pump is not on, the level in the tank will be remain the same. The height will remain the same because qi and q out are equal in that case. Now let us assume in a very ideal condition, like lucky condition, the amount of water you're putting in to the pump, as well as you have opened just the correct amount of taps such that the same amount of water is flowing out, then what will happen? Equal amount of water is flowing out, equal amount of water is flowing in. So the height will still remain the same. Okay. So this is what has been assumed. Hmm. This is what has been assumed. Now, what you have to do is you have to now you have to linearize. Now what you have to do is you have to linearize around an operating point. You're linearizing around an operating point. So basically what you are doing is your qi, you're writing it as qi 0 plus some delta qi. Okay. Your q out, you're writing as q out 0, that is your steady state value, plus delta q out. Your height, you're writing as h steady state value plus some delta h. Okay. And that you will substitute into this equation. Okay, you substitute into this equation. And what you will get? Let us see. Okay. So this equation is d of dt h. So it is h naught plus delta h is equal to minus mu upon a square root of h naught plus delta h, right? Plus qi 0 plus delta qi. Okay, so this is your equation. Now what do we do? Now h naught is a constant. Okay, your height had reached some value, so it is constant, right? So that steady state values are constant. So the derivative over that steady state value is 0. That derivative is 0. Okay. So now what you will get, this will be d of dt delta h. Okay. Now what I will do over here, I will do minus mu upon a square root of h. I will do, let me do this, will be easier. So this is h naught into 1 plus delta h upon h naught plus qi0 plus delta qi. Right? So this I will write as d of delta h by dt is equal to minus mu upon a square root of h naught into square root of 1 plus delta h upon h naught plus qi0 plus delta qi. So d of delta h on dt. Okay, so this also one more point I forgot to add. When you reach steady state operating point, your qi0 is equal to q naught 0. Okay, so what you will get is this minus mu by a square root of h naught will be equal to qi. So you will get minus mu by a square root of h naught plus qi0 is equal to 0. So your qi0 is equal to mu by a square root of h, or your q out 0 is equal to mu by a square root of h naught. Okay. So q out 0 is mu by a square root of h naught. Now if you see this derivation, right, this minus mu of this is now, so now we have what is known as, there is a thing known as 1 plus x. Okay, if it is raised to half, and it is under the condition that my x is very, very less than 1, then I can approximate it as 1 plus half x. Okay, this is an approximation which is used. So what we do is, this can be written as minus mu by a square root of h naught into 1 plus half delta h upon h naught plus qi0 plus delta qi. Okay, so that means my d of delta h upon dt is equal to minus mu by a square root of h naught plus, okay, this minus mu by a square root of h naught by 2 into delta h upon h naught, right, plus qi0 plus delta qi. Okay, so if you remember, if you recall, this actually is equal to qi0. They get cancelled. So my d of delta h upon dt is equal to minus mu by a into 1 by 2 into 1 upon root h naught into delta h plus delta qi. So my d of delta h upon dt, this is a constant a delta h plus delta qi. The constant a is minus mu by a 2 root h naught. So then we can write, so then this is again a linear system, right? So this is d delta h upon dt minus a into delta h is equal to delta qi. Or we can write, this is my x state, x1 is delta h, and my x actually is just x1, and my u is delta qi. So we will get my dx by dt is equal to a into x plus u, right? So this is like the linearized equations. All right. So any issues with this? Okay, so Bindu KP, like what are the two NPTEL courses you are currently doing? You're multitasking.
Sir, it is a course on robotics, sir. Advanced
Okay.
robotics.
Okay.
And the same course which I'm doing now. And also I'm having the course on research methodology also, sir, at the same time.
Oh, like why do you have so many courses? Like why have you enrolled in so many courses?
Sir, as a part of the PhD, I have to enroll 2 courses. So the two
Okay.
courses which I have opted are these two. And the research
Okay.
methodology is the course which is done, which is given by the college. So they conduct the
Oh,
online class, and today I have the online quiz for that also, sir. Everything came on the same time, so I couldn't
okay.
focus on any of the.
Oh, so you're
So that is the
pursuing
issue.
PhD from
So,
where?
sir, NIT Calicut, sir.
Okay. That is
Sir, it's the part-time
Kerala, no?
PhD also. So in between,
Sorry?
I'm doing my part-time PhD, sir. So in between, I have my college for course. So that is not
Oh,
coming in this time. But
okay.
the two courses, the live session came on the same time. So I'm finding it difficult.
Yeah. It will be difficult actually. Previously
Sir,
also.
I want to attend the course also. That is the I want to attend the session also because the assignments are little bit tough. So if you are attending this discussion session only, we'll be able to do the assignments. But
Yes.
I cannot.
Yeah.
That's the issue. Sir, will this sessions will be there on or only on Mondays or like?
Yeah, the sessions will be only on Monday actually. This is the slot which
Okay.
has been decided, 6 to 8.
Okay.
Yeah, because we
Okay,
also
sir.
have different TA duties, etc.
Okay.
So
Okay.
Monday
Okay.
is a
Then.
day selected.
Okay. Then.
Yeah.
Okay.
Anyway,
Sir,
like,
one thing I'm planning is that I'm
uh,
recording the screen also so that later on I can. But if you're sending the YouTube link, then it is okay. So that we can access
yeah.
the YouTube link also.
Yeah. So every NPTEL doubt clearing session by the guidelines, it has to be recorded and that will
Okay.
be uploaded on YouTube. So you then don't need to worry. So for my course and
Okay,
for the
sir.
other person's course also, they will be recorded
Ah,
and it has to be uploaded.
okay. Okay, sir.
So that you don't worry.
Okay, sir.
Good. Yeah. So like over here, like the main part which I wanted to stress out was this one. Okay. Like how is this happening? Okay, like this approximation has to be used. Then only we can linearize, right? So if and now this also is very important that x should be less than 1. That is why I have divided by h naught. The assumption is my delta h is very less than h naught. Okay, so it is very negligible compared to h naught. So that is the approximation. So all these linearized systems, they are not very accurate. Okay, they are just a approximation. Okay, and that approximation is around that particular operating point. So this is done over here. Now, like what else Sir has taught? This is what Sir has used, right? And this is another numerically operated control valve, which is something similar. So that's done. And this is actually a linear system was there. So this is what Sir did. Next, I'd like to touch upon this part. L03. Okay. So I'd like to touch upon this continuous stirred tank. Okay, this continuous stirred tank. So another thing is you're from which department actually, Bindu?
Sir, I am actually from the mechanical engineering department, but my MTech is in instrumentation control system and BTech is in electrical and electronics, sir. Since I am doing
Okay.
my PhD work in robotics, I've come under my research is under mechanical engineering department.
Okay. Okay, so you are electronic engineer, then you're doing control and instrumentation, then you're doing now mechanical, right?
PhD in robotics, sir.
Okay, PhD in robotics. Okay, very multidisciplinary.
Yeah, yes, sir.
Yeah, exactly. It would might be a bit difficult, na, to understand concepts of different fields, or it's manageable. Okay, so I'll teach the continuous stirred tank. Okay, so here we have two feeds, like we have a liquid coming in from here, a liquid coming in from here with some concentration C1, another concentration C2, and then both the liquids are the same. You see, like either both are water or both are oil, both are some honey, assume. Okay, and then we have a stirrer which is stirring very fast. All right. So now, if you see over here, there are two inputs, and there's outflow, which is one output, and the concentration C also is an output. And it is stirred in such a manner that what they are trying to do is they'll have uniform concentration in the tank. Okay, this is something which they want to get. There's a uniform concentration in the tank is assumed. So Sir has derived these equations. dV of t of dt is q1 plus q2 minus q naught, and dc of t vt is given by this expression. Okay, so this is like a continuity of flow and mass balance, etc. So let us write down these equations and let us hope it gives us some particular understanding. Hmm. So these are the equations. We have dv of t of dt is equal to q1 of t plus q2 of t minus q naught of t, and d of dt or c of t and v of t, this is equal to c1 q1 of t plus c2 q2 of t minus c into q out of t. Okay, minus c of t, q out of t. Okay, so these are the equations, and also we have the q naught of t is given by this expression mu into square root of h. So this is mu to square root of b of t upon a. Okay, so these are the expressions. So what do we do? The q naught of t, we substitute both of them. So we will write dv. I'm dropping the t expression. So this is q1 plus q2 minus mu square root of b upon a. Okay, this is q1 plus q2 minus mu square root of b upon a. So what is done? First of all, let us understand that this is two inputs are there. There are two inputs. There are two outputs. And also, is this a linear or non-linear system? Okay, so this is actually a non-linear system. No, actually, Bindu, it's actually a non-linear system because of the square root. Okay, so since this is a non-linear system, we have to be very careful. And what we do is we consider some perturbations, some changes. Okay, so this is so the we replace it by some DC value or the steady state value plus some delta V. Okay, by Q1 I represent by the actual steady state value plus a delta Q1. My Q2 I represent by the steady state value Q2 plus delta Q2. Alright, so where and my C I will represent it by capital C plus delta C. Okay, so these are the certain assumptions which are made. These are the certain assumptions which are made. And then when you write it down, what you will get is uh, so d of dt, capital V plus delta V is equal to Q1 plus delta Q1 plus Q2 plus delta Q2 minus mu 1 square root of A into square root of V plus delta V. So the same thing. My V is a constant, right? So it becomes d of delta V of dt. This is equal to Q1 plus Q2 plus delta Q1 plus delta Q2 minus mu upon square root of A into square root of capital V into square root of 1 plus delta V upon capital V. So again, my d of delta V of dt is actually Q1 plus Q2 plus delta Q1 plus delta Q2 minus this mu of square root of V of A into 1 plus half delta V upon capital V. Okay. So then what is done is this Q1 plus Q2 minus me write it completely. So this is a d of delta V of dt. This Q1 plus Q2 minus mu square root of V upon A plus delta Q1 plus delta Q2 minus mu square root of V upon A into delta V upon capital V. So I'd like you to understand this at steady state. At steady state, what is my Q naught? My Q naught is mu into square root of V upon A, right? And at steady state, what? The inflow, the rate inflow is equal to the rate outflow, right? So that's why my Q1 plus Q2 is equal to Q naught, and this is my Q naught expression. So these two will cancel out each other. So my d of delta V of dt actually will be equal to delta Q1 plus delta Q2, and this minus mu square of V upon A is my Q naught. This minus Q naught into delta V upon capital V. Okay, any doubts in this? Okay, right. So now what we will do, now we will do for the next set of equations. What is the next set of equation? D of dt CV equal to C1 Q1 plus C2 Q2 minus C of U out. So here what do we do? C we represent by capital C, that is a steady state operating point or the steady state DC value plus delta C. V again we represent by capital V plus delta V. Q1 we represent by capital Q1 plus delta Q1. And Q2 we represent by capital Q2 plus delta Q2. Okay, so I'll write it down d of dt C plus delta C into V plus delta V is equal to C1 to capital Q1 plus delta Q1 plus C2 capital Q2 plus delta Q2 minus C plus delta C into Q naught plus delta Q naught. Okay, so I'd like to highlight something specifically. So now, if let us see this point, we have this C plus delta C into V plus delta V. We can write it as what? CV plus V into delta C plus C into delta V plus delta C into delta V. What we do is we ignore this. This is negligible. This is an approximation we take because delta C and delta V are quite small. So delta C into delta V will be small. Like let us assume delta C is, let us say, 10 to the power minus 2. Delta V is 10 to the power minus 2. So if you multiply delta C into delta V, what you will get? You will get 10 to the power minus 4, which is even more smaller. Can we assume delta C is much smaller than C? Delta V is much smaller than capital V. So this way the product of delta C into delta V is also very small and negligible. So this is a assumption which holds valid under certain conditions. Okay. Similarly, we have C plus delta C into Q naught plus delta Q naught. We again write as C into Q naught plus C into delta Q naught plus Q naught into delta C plus delta C into delta Q naught. Again, this is negligible. Okay. So we use this approximation in this equation. So what do we write it as? D of dt into CV plus V into delta C plus C into delta V is equal to C1 into Q1 plus delta Q1 plus C2 into Q2 plus delta Q2 minus of C into Q naught plus C into delta Q naught plus Q naught into delta C. Okay, so this is the expression. Now again, CV is constant. So it becomes D of dt into V into delta C, the C into delta V is equal to C1 Q1 plus C2 Q2 minus C naught Q naught plus C1 into delta Q1 plus C2 into delta Q2 minus C into delta Q naught minus Q into Q naught into delta C. Okay, so this we can write it as V into D of dt delta C plus C into D of dt delta V is equal to C1 Q1 plus C2 Q2 minus C naught Q naught plus C1 delta Q1 plus C2 delta Q2 minus C into delta Q naught minus Q naught into delta C. Okay. So this part will be 0. Because in steady state, what happens is, in steady state, what happens? Where is that? This dc of t, v of t actually is the rate of change of mass. So in steady state, what happens? The mass is approximately constant. Okay. So the C1 Q1 the C2 Q2 minus C of C into Q naught will be 0 in steady state. So that is why this expression will be 0. Okay. Now what we can write it is V into D delta C by dt plus C into derivative of delta V of dt is equal to C1 delta Q1 plus C2 delta Q2 minus C into delta Q naught minus Q naught into delta C. Right? Now we already found this expression. This expression we already have. Right? Let us say this is the expression we have. So we'll substitute that. So this is given by, so this V into D of dt delta C remains the same, plus C into, what is this expression? Delta Q1 plus delta Q2, delta Q1 plus delta Q2 minus Q naught into delta V upon capital V is equal to C1 delta Q1 plus C2 delta Q2 minus C into delta Q naught minus Q naught into delta C. Okay. So this we will further write it as V into D of T delta C plus C delta Q1 plus C delta Q2 minus C into Q naught delta V upon V is equal to C1 delta Q1 plus C2 delta Q2 minus C into delta Q naught minus Q naught into delta C. Right? So any doubts still here? Okay, this is getting really very difficult. So what do we get finally over here is v d of dt delta C is equal to delta Q1 into C1 minus C capital C plus delta Q2 into C2 minus capital C. Then you have this minus C into delta Q naught minus Q naught into delta C plus C Q naught upon V into delta V. Okay, so here we have dc by dt is delta Q1 upon C1 minus capital C upon V plus delta Q2 upon C2 minus capital C upon V minus Q naught upon V delta C minus C delta Q naught upon V plus C Q naught upon V delta V. Okay. Let us check. Okay. We have forgotten minus Q naught by 2. That will be equal to minus Q naught by 2 delta V upon V. So minus Q naught by 2. So just hold on 1 minute. Okay. You have doubts regarding assignment questions? That's all. So what doubt you have regarding the assignment questions?
Sir, what is the difference between this general dynamic system and linear dynamic system, sir?
So this, like if you see, this is your general dynamical system. Okay, this is like your general dynamical system. But your linearized dynamical system is the one. Okay, let me say for the one which we have done properly. So over here, okay, open time system. This is the dynamical equations. Okay, this is the effective dynamical equations. Then what do we do is we linearized it. Okay, when we linearized it, this is the expression which we got. Okay, this is the expression which we got. So this is the expression for the linearized dynamical system. I hope that's also your query.
Sir, the question was like in standard state space representation, the general dynamic system, the first derivative of the state variable, that is state equation, is a combination of like state inputs, time, like that.
Yeah.
What is
Yes,
the
yes.
difference in general dynamic system and in linear dynamical system? How will be the state equation?
Like in linear dynamical systems, it is linear, right? But in a general dynamical systems, it is non-linear. This is non-linear. Hmm.
Okay. Sir,
Yeah.
whether in general dynamic system, whether there will be a function of time, or how can we write like from this equation, how can we clarify whether it is a function of time?
Mm, function of time.
Nonlinear function of state and input, or a nonlinear function of state, input, and time. That is the confusion which is coming.
Mm-hmm. See, first of all, I'm actually not supposed to discuss the assignment questions.
Okay,
Usually,
sir.
what happens is it would be like since this course is being run for the first time or the second time, that's why like we have to just teach and I have to solve some questions of my own. Like, but in
Okay.
previous, but in different NPTEL sessions, what happens is they have the assignments of previous years. So that is what is solved.
Okay, sir.
Okay. So
Okay.
there's a special case, and this also my like I have conducted NPTEL sessions for courses which are being rerun multiple times, but this is
Okay.
the first time I'm
Okay.
doing for one. Yeah, so I'm not actually allowed, so I cannot
Okay.
exactly tell. That's the thing.
Okay.
But
Sir, from
okay.
that representation of the state equation, it
Mhm.
is not clarified. That is my doubt. Whether, like, if you write it like x dot is equal to ax plus bu,
Mhm.
if it is for time variant system or if it is for time invariant system, we can say that it is not a function of time. But from the options, we are getting it confused whether it is a like function of state input and time is also coming.
Mhm. Yeah, that is a tricky thing. If it is time variant or time invariant, then that they have not specified, right? That is the
Yes, sir.
problem. Mm-hmm.
So in the class also it was not specified. When we go through different textbooks also, the concept is not clear. I have read multiple books, but it's not written in a like we are also getting confused. We see the
Yeah.
options.
Mm. I have a kind of feeling that it's like in these equations or the examples which sir has specified, they're not explicitly functions of time. Okay. But I don't know
Okay.
exactly what is the question, what it specifically wants from you. But I can see from the examples which sir has done, they are not exactly functions of time. Like they're dependent on time, but it's not like a function. Like it is not A
Yeah,
into
yeah, yeah. That
B
that
or something
concept is
like that.
the that concept is a little bit confusing, sir.
Hmm. Yeah,
They are
yeah.
depending on time, but whether we can say that it is a function of time, that is the
Hmm.
thing we are getting confused.
Yeah, yeah, yeah. Yeah. Actually, you can post this doubt in the forum. There's a Google Groups, right? For this, I was just checking today. So each NPTEL course will have a Google group which you can join, and they have actually posted a message that please introduce yourself, etc. So you can introduce yourself, and then you can
Okay.
post it out and everything, right?
Okay.
And
Okay,
to my
sir.
knowledge, like no one is allowed to exactly tell you the answer. Yes,
Okay.
any
Okay, sir.
conceptual doubt, that is what we have to help in debugging and like kind of discuss and kind of like brainstorm. That's our point.
Okay.
Part.
Okay. Okay. Okay, sir.
Okay. And like, are you the only one from your college doing this course, or there are others also from your college doing this course?
Sir, I'm not sure whether anybody else is doing the course, but not sure. I didn't get the
Hmm.
clarity regarding that.
Hmm. Okay, okay. Yeah, yeah, fine, right. Okay. Then you can like you can see any other doubts you have regarding what I taught, or like Is it like going too slow? Anything can give the feedback, because certain things I took my time to try to explain to you guys because I felt that those are the foundations. So do you want me to go faster or slower? Something?
Sir, it's okay, sir. Good class, sir. It is good.
Okay. And like, should I do those MATLAB demonstrations, or like should I just teach the theory and other things?
Sir, MATLAB demonstrations are also useful, sir.
Okay. Then I'll continue with that because I also find it interesting. Like 2 hours just writing is like kind of irritating everything, and MATLAB is kind of something where you can see the result. And I'd actually recommend that you can kind of like verify your answers as much as possible using MATLAB. Although that you can't do in exams, but while studying, etc., you can kind of verify it if you have the parameters, everything.
Sir,
And
the questions in the exam will be objective type or like how will be the questions?
uh, like it usually be objective type as well as numeric answer types, where you have to give the value, like you have to solve the sum, and based on certain values, you will give the what you say, the answer. Like you say that the mass is equal to this, or the flow is this much, etc. Currently, in the assignments which have been done till now, in assignment one, there is no, I don't think there's any numeric answer type thing. But in assignment zero, I think there is. Assignment zero also, there's no numeric answer type. There are options. You have multiple choice options, right?
Yes, sir. Yeah.
But in the previous NPTEL courses which I taught, like network analysis, etc., they had to solve, and they had to find a current, and they had to find, let's say, the current through the inductor for, if it is 2.9834 ampere something, they will say to specify to which point, to 2 points, etc. So then they have to write 2.98 ampere, like that.
Okay.
Hmm.
Okay, sir.
Okay, if you don't have any doubts, we can end this session, right? So what I'll have to just check the derivation, what has gone wrong in the last. I think there's something I've skipped. You have to check this. Okay, so I'll end the session. Okay, thank you for joining.
Okay, sir. Thank you, sir. Thanks, sir.
Thank you. Bye. All the best.